The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Hey, welcome back. Hey, we have an interesting interview today with
We sure
Jessica.
do.
Yeah, Jessica Pointing. She's pursuing her PhD at Oxford. We'll give a longer intro in the main episode, but impressive person. But this whole context, right, of this paper, I saw it fly by on my Twitter feed, and I'm like,
That's right.
that looks kind of interesting, and read it in more detail, just the abstract. And I was like, we really ought to do an episode on this one. So there's just a rich context here. Where I think at a fascinating time, right, in the intellectual history of these ideas around data science, classical machine learning, quantum machine learning. So there's much of the frontier left to reveal. So
Absolutely.
Jessica gets us to I think a next level understanding of what this all means and does.
Yeah, I'm really excited by this conversation, Kevin. As you said, we're at a particularly interesting moment in the history of classical machine learning. Things like OpenAI and the rest of those technologies are certainly dominating the headlines and the investment landscape, and a lot of interesting topics of discussion around the progress that's being made or is not being made, or what the applications may be. And then straddling that over into the level of uncertainty we have about quantum computing, it could be one of those topics can be perplexing. The two in combination are completely baffling. So I'm hoping that Jessica can help shed some light on our understanding here.
Good stuff. All right, here we go. And welcome back. Hey, it's Kevin Roney. Hey, Sebastian, how are you, man?
Hey, Kevin.
Hey, so today we've got a really interesting interview with Jessica Pointing on this, I think, fascinating new result on some of the trade-offs, limits, and possibilities with quantum neural networks. Our guest today is Jessica Pointing, who's now pursuing a PhD in physics at Oxford. Previously, she was a PhD student at Stanford in CS. And wow, she just goes back and back, more and more impressive resume achievements. Time at Harvard and MIT. I think she's had some experience at Google, McKinsey. Just an impressive array of achievements. Cited as selected as a Forbes 30 under 30 in science. So hey, look, so many more. It's almost overwhelming, but very impressive, Jessica. Welcome. Welcome to the podcast.
Thank you. Thanks for having me. Glad to be here.
Well, look, the thing that really had us pursue you for being a guest on the show was your recent paper called "Do Quantum Neural Networks Have Simplicity Bias?" And so, what we're trying to do often on this podcast is both embrace, some of the optimism of the possibility of quantum computing, but see it, in a very sober way. There's too much hype, and I think delving down into results like these, I think, helps set expectations and position, the whole space for future growth. So, Jessica, let's begin with the context that brought you to this new result.
Yeah, thank you. I agree that it's good to sort of have this understanding of both the sort of advantages and possible disadvantages of quantum at the moment and the current state we're at. So I think it's sort of interesting actually to start from the context of just classical machine learning. As you can see, it's crazy what's going on. We'll take, for example, ChatGPT, I think, is one of the fastest consumer growing applications with, estimated 100 million users within just a couple months after launch. And I don't know if, maybe the popular, just the public, if they understand that actually the underlying technology is neural networks.
Yeah.
And neural networks have a sort of a history, but I will sort of focus on particular this idea of the bias-variance trade-off, because that's sort of one of the things that has been sort of in statistical learning theory, sort of one of the bases that people have been thinking about. But maybe so the bias is basically, we humans have a bias. So for example, if I'm going on Amazon and I want to, I want to buy some headphones, and you get hundreds of items, and maybe my bias is to choose the cheapest item, for example, or I have a bias towards something that's cheaper.
Or maybe you're an Apple fanboy or something.
Exactly. Or maybe, you have a bias towards a particular brand or something. And so a bias is basically a set of assumptions that one makes. And we see that neural networks, so they're basically a machine learning model. And a model is basically a program that has been trained to find patterns and make decisions on data. And so we see that neural networks have a bias as well. And so we can also look at this other sort of property called the variance. And that sort of is telling us how spread out the data is. And so it's seen in statistical learning theory that there's this idea of this bias-variance trade-off. So basically, if you have a very simple model, there could be an error with predicting the right outcome because it's too simple. But if you have a very complex model, so that means there's high variance, then there could also be an error because you're fitting the very particular parts of the data that you're training on. So for an example is, if you only, let's say you have images of cats and you only take images of cats when it's outside, so the sky is blue or something. And then maybe the neural network model now thinks that whenever it sees a blue sky, that's a cat.
Must be a cat.
Right.
Yeah. So it's also it's training for that particular that particular data that you trained it on. So there's this idea of this bias variance. Yeah. So there's this idea of this bias variance trade-off that people thought was the case, but actually we have now deep learning, which is basically neural networks with many layers, and it's actually found that this bias variance trade-off doesn't deep learning basically defies this. It doesn't really sort of apply. And if people are looking at a visual representation of it, there's this double descent curve to sort of visually represent it. But basically the idea is that actually in deep learning, what happens is you sort of have these very complex models that can fit exactly the data that you're training on. But then it's actually still able to generalize well on data that it hasn't seen. And generalization is basically how accurately it can predict the outcome value for unseen data. So so this is sort of kind of a dilemma or a sort of a question as what's going on? Why are deep neural networks able to do this? And so there are a couple, and that's actually why it's kind of exciting, because I would say there isn't a strong consensus on why this is happening. Even though this technology is being very widely used, we still don't really understand the fundamental properties of it. And is where
it's hotly debated right now. Yes, I mean, guys like Hinton, one of the founders of this whole field, talking about how these machine learning algorithms, they're almost like a blanket that could be draped across a complex shape and capture most of its nuance. And there's others that dispute, right, whether or not that's the appropriate intuition. So you're right. There's still deep mysteries, it seems, in this domain.
Yeah, exactly. Which is quite fascinating because it's been so widely used, right? And I think some of the problems we have today with AI can stem from the fact that we don't really fully understand what's going on with these models.
Yes. Yeah.
So as you can see, it's an important sort of thing to look at. And so there is a group at Oxford. So they have a theory which comes to this idea of simplicity bias. So their theory is that basically that these neural networks have a bias towards simple functions. And so that is and most real world data is simple. And when I say simple, you can think of it has a structure like symmetry, for example, or so. And because most real world
I guess
data,
there's the so-called manifold hypothesis by what's his name, Joshua Bengio, right? I mean, that somehow a high dimensional data set has a thin lower dimensional concentration of where the truth lies.
Yeah, so you can think of it like effective dimension. So for example, if you have like the MNIST data set, which is like basically handwritten digits, it's like 28 by 28, but if you actually look, people actually think it's a very small subset of those pixels that are actually sort of maybe a very simple example is if you have like a 3-dimensional space, but you have like 2 data points that are on a 2D line, then the effective dimension is 2, even though it's like in a 3D space.
Yes, right.
So there's this idea. So basically real world data is sort of has structure and is simple. And so they showed that deep neural networks also have this simplicity bias. And I mean, you could even go into philosophy here, right? With Occam's razor, right? Is the idea that we should have this bias towards simple solutions. And so it's interesting that neural networks seem to have this bias towards simple solutions. So this brings, interesting questions about quantum neural networks because
and that's just the context of the classical case.
Yeah, that's the context.
And there's even more interesting like frontiers right down to the quantum machine learning. So sorry, continue. Just trying to set some milestones here.
So that's sort of the first milestone is just this idea of simplicity bias, and then the second is sort of looking at quantum neural networks. So we know that they're inspired by neural networks, but they are sort of different in some ways. And there's a lot of questions about what quantum neural networks are useful for, and
it seems like there's many people who are still standing on the sidelines, quite skeptical. They could be optimistic about QC in general, but still really questioning whether or not there are room for progress in this domain. There's been many attempts at finding huge breakthroughs over classical algorithms on time complexity advantage. It's hard to point to a big result yet, right?
Yeah, exactly. As you said, like in just quantum computing, we know we have these sort of advantages in terms of complexity, and some of that has been mapped onto the sort of the space of quantum machine learning. But now you see a fundamental difference because in machine learning, in classical machine learning, sort of it's all, we're dealing with benchmarking, we're dealing with empirical results. There aren't all these theoretical underpinnings. But in quantum computing, the sort of the underpinnings have been mostly like theoretical because we have to sort of justify like why we're doing this.
Yes, right.
So quantum neural networks comes in this weird sort of place where, maybe we have empirical results, but we also have complexity arguments, and we're not really sort of quite sure what it could be used for. So I think when I read this paper on simplicity bias, I guess, that was sort of the motivation, was to understand, well, okay, has anyone looked at this in quantum neural networks? Because if simplicity bias is maybe one of the reasons why classical neural networks work well, maybe it can give us an insight into whether quantum neural networks can work well on like real world data and classical data. So that was the sort of motivation. And then I guess then sort of what we find is maybe going into a little bit more of the specifics, but
for your paper now.
So in terms of the quantum neural networks, so I think there's 3 sort of different sort of parts of a quantum neural network, and sort of I should say this is the standard architecture. So first you have like the encoding circuit. So this is how you sort of actually encode the data into the neural network, because if you have classical data, there has to be a way that you put the data into the network. And then you have this variational circuit, which is basically where you're changing the parameters to sort of fit some cost function. And then lastly, you have like the measurements. So
and you have a classical loop on the outside, assisting with gradient descent on the internal quantum computing component of the loop.
Yes, you're correct. So that's the sort of the actual optimization stage is, so you can use a classical optimizer to optimize the parameters. And you could even actually evaluate the gradients on a quantum hardware, but that's like another thing, but that's not as practical. So, we have sort of that sort of framework. Now, basically what we show is, and some papers have sort of kind of shown this through other ways, but that the encoding method is really sort of what changes the inductive bias, bias, of the quantum neural network. So this is the main sort of kind of the main part of the quantum neural network is really sort of the way that you encode the data into the neural network. And that's really important for understanding like what the bias is. And so we were interested to see if, what type of bias we could get and if you could get this sort of simplicity bias. And so what
it's an active area of interest, right? I mean, all the numerous ways of doing encoding, right? I mean, there's spectacular amounts of attempts, right, at finding new representations that might create this breakthrough. Still, I don't think they've found yet compelling evidence of some basis that's going to create a huge advantage in QML. It's an open question, so it seems like your paper makes valuable contributions to this exact question.
Yeah, exactly. Yeah. So there are some papers that have sort of come up with different encoding methods or try to look at them. And so we sort of we look at it through this angle of sort of simplicity bias and seeing what happens there. So in particular, we look at Boolean data. So just like 0, 1, 0, 1s, because it's sort of easier to sort of make a statement about the property of the data. So we can say, what is the complexity of the data? So for example, if I just have a string of 0, 0, 0, 0, then that's sort of, we call that's very simple because, it's just, I just say, oh, it's 0 repeated, how many times. But if it's something very like 0, 1, 0, 1, 0, 0, 0, 1, something very like random, and so then that has a high complexity. So we want to see sort of what sort of functions does the quantum neural network produce? Like, does it produce something that's like simpler or more complex, and what probability? So that's what we look at, and we find that we look at a range of different encoding methods, but I'll sort of highlight the main ones. But the most basic way of encoding the data is just in the state of the quantum bit. So, for example, if my data is 0, 1, I just put it into I make the quantum bit 0 and I make the other quantum bit 1. And so this is called basis encoding. So it's the most basic type of encoding. And so other papers have shown this too, but there's basically no bias with that. So basically it means it's kind of a random learner, because if you have no bias, it's sort of like you're just randomly picking something.
Right.
So going back to the Amazon example, if I have no bias, I'm just going there's no way for me to choose what headphone I'm going to choose. I'm just going to choose something random. You're just
meandering at random around the state space. Yeah, right.
Exactly. So so that basically means it's not really effective as a learner because it's not going to learn anything. But the thing is, if you can actually restrict the expressivity. So basically the expressivity is what sort of functions can it actually express. So this is so going back to the 0, 0, 0, 1, 1, 1. Maybe there's it can't express all zeros, or it can't express all ones. So the way that we build the quantum neural network, it depends on what sort of functions it can express. And if it can't express those functions, then it means it's going to be hard to sort of learn on that. So what we find is that you can restrict the expressiveness of the quantum neural network, and that can somehow introduce some sort of bias, but it's sort of artificial. The way I think of it, maybe intuitively, is going back to the Amazon example. If I say sort of I have a budget and I'm I'm only going to look at headphones below a certain below $50 or something, then there is some sort of, if you look at the whole, all of the items, then there is some sort of bias, right? There's a bias towards the cheaper ones, but then it's because you're not able to even express the ones beyond that. So
I see. Right.
Yeah.
And if I'm not mistaken, inside your paper, you're using really two measures, right, to zero in on these features. It's Shannon entropy, right, and LZ complexity. Do I have that right?
Yeah, you're correct. So the reason this goes into a little bit of other things, but those are those are the two measures. It's like it's a whole rich thing, but
It goes deep.
Basically these are measures to sort of measure the complexity of the Boolean string that I talked about. So
Right.
And we wanted to distinguish between entropy and the LZ complexity, because the LZ complexity is maybe more of a maybe truer way to see the actual complexity of the string, but whereas entropy is just looking at like the frequency of zeros and ones in the string. So
Right.
it's a bit more trivial. So we wanted to distinguish between those two.
And thank you for tolerating all my tangents here. I'm just trying to
of
prompt
course, yeah.
questions to illustrate key points for the audience. So please continue. Sorry for my interruption.
No, thank you. So we have the basis encoding, and then I think the real encoding methods that is interesting is the amplitude encoding, because we actually showed that there can be a simplicity bias with amplitude encoding. So this is basically where you put the data into the amplitudes of the quantum state. And then we do see simplicity bias, but then we show that actually the expressivity of it is reduced. So it's not able to express certain functions. And it's quite interesting because actually, if we go back to just classical machine learning, the perceptron, which is basically just like a single layer neural network, it's like the building block of neural networks. There was a paper by Minsky that showed that the perceptron could not
classic story.
The perceptron couldn't express the XOR function, which is basically the parity function for two. So basically the parity function is you have one if the input has an odd number of ones. But anyway, but this sort of kind of prompted this AI winter, because people were like, oh no, it can't express.
It was catastrophic for the machine learning agenda. Yeah.
Yeah, exactly. So, but it did obviously spur on research to sort of come up with multiple layer neural networks and actually see that we could express more functions. So I think so. Kind of in a similar way, the amplitude encoding, it can't express the parity function. And actually, if you go beyond, if you go to high levels of qubits, there are more functions it cannot express.
And that's a really basic operator. I mean, if it can't get to that, even its simplicity is obviously too extreme to an extent, right?
Yeah. So as you can see, that sort of it's kind of a little bit of an obstacle to becoming a general purpose learning algorithm, because the thing is, and so I think this goes back to the context of the beginning, is that deep neural networks, they're able to be highly expressive, and they're able to have this good bias towards simple functions, which enables them to generalize well on data that they haven't seen. But I guess our paper is suggesting that there is this sort of trade-off with the encoding method that you use, that if you have a good inductive bias, like the simplicity bias, but now you don't have good expressivity, or if you have good expressivity, like the basis encoding, now you don't have a good inductive bias. And that's sort of a bit of a problem for general purpose.
Problem. I mean, you really have to have both, right? I mean, there's just no other way.
Yeah, at least to be comparable to deep neural networks, because because if deep neural networks are able to do this, then and most real world data is simple. So a quantum neural network, if it wants to be a good general purpose learning algorithm on real world data, it should have the expressivity and this sort of simplicity bias. At least that's what we claim it should.
And so the paper covers the amplitude basis. It covers the canonical basis. Any other bases in the scope of analysis here?
So we do look at some other encoding methods. So we look at this one called the ZZ feature map, which is sort of a popular one based on this other paper on supervised learning with quantum enhanced features maps. And we also look at this other one, which is just basically like kind of a random non-unitary transform. But I mean, that's going into the specific. But we show that these have like a trivial bias, so they're not as interesting. But what is kind of, so the ZZ feature map, actually it does have a bias towards the parity function, in some sense, which it was sort of designed to do. And so this actually raises like another point, which is that you can actually always create an encoding method that has a bias towards the thing that you're looking for.
Yes. Yeah.
So you can do that. But the thing is, so
is it general? Yeah, right.
right.
Yeah,
so
general,
and
right.
So I mean, and that's what kind of happened in classical machine learning. I mean, first you're kind of hand encoding sort of the problem into the thing, but now we've kind of moved past that, because we don't need to do that anymore, because you can just like take a neural network and it's just so general, it applies to most problems. So I think
you're cheating the bias-variance trade-off there, right? By overfitting on one particular use case and blowing the rest.
Right. So so I think that's the thing is, and this kind of goes into sort of the cases where we see quantum advantage. Basically, they do this. They take a particular problem that they know may be hard to do classically, and then they create an encoding method, essentially,
to targeted right at that problem.
Yes, has a bias towards that particular problem.
I see.
And then it's able to do well, which is good.
Self-fulfilling prophecy.
Yeah. But I guess like the good thing is they do show that, it's hard to do that in a classical setting, but it's easy maybe if you had an ideal quantum computer, like the fault-tolerant quantum computer. So I think there is obviously is like good research to do that. But as you can see, it's like for very specific cases. So yeah.
And so this is I think the crux of the matter for me. I mean, so help me understand. I mean, it looks like you're doing this fairly detailed analysis of sketching the possibilities and limits, right, with these QML algorithms. And I think you're working within a framework, which is, this, variational quantum ML. I mean, this is it's got broad generality across the entire space. And you seem to be sketching out this possibility that numerous of these bases just won't do the job. And so the question I guess I'm coming down to, and maybe I'm going out on a limb here, I don't want to put you in an awkward spot, but I mean, is it possible that this paper sketches fundamental limits, right, on the eventual merit of quantum machine learning?
Yeah, I mean, I think there are other papers that have sort of definitely kind of gone in this direction, and sort of hinted at this in different way, or like come at it from different angles. And I think sort of the paper it is sort of, I mean, we haven't like proved this sort of bias expressivity trade-off or something. So I do think there would maybe need to be more research done to sort of really see if this is sort of something that is like very fundamental to the frameworks that we have.
Attribute of the space, right? Versus some finding that is applicable on some scope, but not general yet. Yeah.
Right. So, but I think our paper sort of contributes to this idea that quantum neural networks, at least the frameworks we have at the moment, are probably not going to be like these general purpose learning algorithms on classical data. And I think, I mean, in one sense, that's like, okay, but I think it's good because it can then lead us towards other alternative directions, which is sort of...
For instance, could it be there's some other undiscovered as of yet encoding that satisfies all these desirable requirements? So it's not just targeted at a particular problem. It's got generality. It's got the right bias. It's got the right simplicity. I mean, is it possible there's just some undiscovered outcome in advanced research to come across a new encoding?
Right, yeah. So, I mean, I think given sort of the literature and what we show, I think it's sort of unlikely, but I mean, you never really know. So it could be possible. I mean, the ideal scenario is you have this encoding method that has a good inductive bias, and it has good expressivity. And then, I mean, that's just to make it comparable to deep neural networks, right? And it has to do something more, which is it has to sort of have some sort of speed up or something, where it's like over the deep neural networks, which at this point, so you can see that's like something very difficult to do, because we don't even have, as we talked about before, like the theoretical underpinning for the deep neural networks to even compare maybe if there is some sort of, exponential advantage or something. And then you also have the problem of, at the moment, the hardware is, very limited, and it's nowhere near deep neural networks. And so, I think this is sort of the ideal scenario. But I think also it's possible that we just look at completely new frameworks for quantum neural networks.
Right.
So this is based on like sort of the standard framework, which I talked about, which is this encoding method and this variational cycling. But I think there could be completely new strategies for doing quantum neural networks. And I think that's probably a bit more fruitful to look at. And so.
Interesting.
That's interesting. So in a sense, what you're saying is that, we've gone through this process of trying to fit what we know about classical neural networks onto quantum computers, at least theoretical quantum computers, which don't exist, and it doesn't seem like there's any inherent sort of performance gain from sort of the simplistic sort of porting of those methods onto a quantum computer. Is that right?
Yeah, sort of. Yeah, I'd say that. Just sort of by using this sort of framework, we're not having this general purpose advantage, but it's only for very specific use cases, which actually at the moment, haven't really shown to be relevant to practice to like real world practical use cases as well. And also they're not.
I guess that's another possible alternative. Is it one narrow but extremely valuable problem?
Right,
that could be discovered a brand new encoding that would nail it on that one, right? That would be
So I think that's an alternative area of research, is if we can find like relevant, useful, sort of very specific use case example, and then you create an encoding method for that. That's also a possibility, but that is yet to be done as well.
Wow, so there's just a whole landscape of really interesting questions ahead, and this paper, again, it seems like it sketches out this fundamental attribute of what is due diligence, right, on cross-checking one's new results in QML, and look at these various trade-offs in ways that really tell the story. Because I think you're right. There's been a lot of results that have been published and hyped in terms of their huge advantage for quantum machine learning. Sounds like a cool topic. And later there's retractions, there's dequantizing, there's all sorts of ugly outcomes here. It's a treacherous space. Again, it just feels like a really interesting framework you've got here to at least help with more rigor and clarity evaluate future algorithms in this domain.
You bring an interesting point about sort of like sort of the claims of a quantum advantage. And as I said, like there are like theoretical claims, which is based on all these like complexity arguments and stuff. And that's good, but it's not really sort of relevant, and it's not available on current hardware. And then you have maybe these claims that have been done sort of empirically, so they've run some experiments. But actually, if you take a closer look at some of these, one is they may make comparisons to very simple, classical deep neural networks, and in some sense, it's a straw man argument, because they're comparing it to something that actually isn't that good. So yes, you get an advantage, but you've compared it to something that's not that good. So if you actually compare it to something that's good, then that's not the case necessarily. And then the second thing is they may use very simplified data sets, and they may use it on very, very small scale. And then it's hard to sort of make arguments about the larger scale when you're looking at the smaller scale. And I think Maria Schuld actually says a lot about this, and she has a lot of interesting papers. And I think she is, I think some of her papers are sort of questioning what's going on in the field. And so, I think she has a paper called, is quantum advantage even the right goal? And so she's sort of saying that, we have this hyper focus on quantum advantage, but it's sort of very limited because of these problems I've just talked about and that she talks about. And she suggests like ways to move forward by looking at alternative things. And like one of them is kind of what I mentioned, like this idea of a new building block for quantum neural networks, kind of a new maybe framework. And then also like keep on like developing the quantum software and then looking at quantum kernels and things like that. So I think there is some sort of people are talking about it. So
a possible future guest, she'd be interesting.
Oh yeah, she'd be great.
Yeah, so far it looks like you've got Grover's algorithm, you've got Shor's. Those are clear breakthroughs for the quantum computing scenario. But it's hard so far to sort of see clearly, right? A big example, prominent example of a killer algorithm that really rings the bell.
Well, and it seems like, as you were saying earlier, Jessica, like we don't really understand how deep neural networks work classically anyway. So their heuristics or our understanding of them is heuristic. So it seems like a massive challenge to figure out how to create a theoretical proof of advantage in a quantum setting for something that we don't really understand how it operates in a classical setting.
Right for the neural networks. And I think there is sort of interesting, so like we haven't talked about like quantum kernels, and that's a whole other thing, but I think quantum the kernels like that is actually interesting because you can sort of sometimes make more of these arguments, and that's actually what some of the papers do when they look at quantum kernels versus like the classical kernels, and then they are able to sort of make these claims of quantum advantage. But the thing is, the classical neural networks have sort of overtaken kernels in the classical setting. Like there's a reason why kernels aren't as popular, because it's harder to scale and things like that. So so it's sort of the many components that like need to be taken into account.
You have the same dilemma, don't you, with kernel methods as you do with this scenario with encoding choice, right? In that there's numerous different kernels you could conceivably choose, finding the best fit against a given problem with adequate generality and time efficiency. Not an easy, trivial problem, that one.
Right. And Maria Scholl's work does this sort of, she has some papers like mapping quantum neural networks to kernels and
that's a cool result. The broad generality of QML reduced to quantum kernel methods.
Which is interesting, and it does help sort of have a better theoretical understanding. But I guess as you can see, there's still a lot to be understood. Which I guess is like what science is, and it's like fascinating because there's all these kind of all of these things kind of coming together, like in classical machine learning and quantum machine learning and just quantum computing and sort of like, I
mean, we could keep talking about this for a much longer period of time, but I'm curious, is this sort of central to your PhD thesis? Is this what you're working towards?
So this is so I've been sort of working on this, and I've done some other projects, which is I did like a project on a quantum compiler, for example, and actually like applying a variational quantum algorithm to an optimization problem in open pit mining, which is kind of a bit cool. Like that was actually trying to find like a real world application. But I'd say sort of my PhD is sort of the main focus has been on this particular problem.
Yeah, such a cool topic. We really appreciate your time, Jessica. Yeah, and thank you so much for giving us this glimpse of the current status of this really interesting time that we live in. There's so much to look forward to in terms of new results in this domain. So, thank you so much.
Yeah,
really
thank
appreciate
you.
it.
Thanks.
Wow, that was so cool. It's just a great, I think, overview, right, of the landscape of the foundations, right, of data science and bias variance trade-off, the huge new breakthroughs, pioneered by machine learning and this whole generative movement and this capacity of these systems to,
Mm.
with simple functions, get to high accuracy on this manifold of truth. That's just the context, right?
Hmm.
of base camp on this huge climb up Everest, so to speak, as towards some possible huge advantage that might be in the future for using quantum computers on the machine learning use case. So, really interesting framework she's got here to help
Absolutely.
you do due diligence on these algorithms.
Yeah, I really appreciated her starting by giving us a foundation in the classical
Yeah.
context. It seems like, as I said, we've got this really interesting moment where deep learning, classical machine learning is progressing, but there's questions about how far that progress is going to take us.
Lots of
We
hype.
don't
Some
have
of it warranted. Yeah. I mean, yeah.
Right, sure. I mean, potentially, right? We don't have a theoretical understanding for how these things work or what their limits are. These systems that are being built by OpenAI, by Claude, by Google, et cetera. And so, it was really interesting to me to understand that level of uncertainty going into the quantum context where we have some theoretical basis for performance advantage in things like Shor's and Grover's and HHL, as you brought up in the conversation, Kevin. But we don't have that kind of generalized understanding in quantum machine learning, and in part that's because we don't have that kind of generalized understanding in classical machine learning. So it's uncertainty piled on top of uncertainty in a sense.
And so, so such cool new frontiers she sketches out as well in
Absolutely.
terms of, could there be, a brand new set of encodings, right, that could be show generality or applicability to a specific set of high value use cases.
Right.
And also there's this whole interesting area, right, of kernel methods,
Right.
which goes deep mathematically, but fascinating topic. So, I think we've got to talk to some more guests in the future on that front. Yeah.
Absolutely. But yeah, this conversation with Jessica was a terrific sort of starting point. We really appreciate her time and her insight. And we look forward to continuing the conversation on the topic in the future.
Super fun.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.